All right, good morning and welcome back to Calculus 2. So today we're going to talk about trigonometric integrals, and I've got a couple of examples that we're going to go ahead and deal with today. So what this really pretty much has to deal with is powers of trigonometric identities that we're trying to integrate and like the strategies that we're going to go ahead and deal with this for them. Okay, so when I'm noticing this piece here, we've got an odd power of sines and an even power of cosines. Really, what you want to do is you want to use these powers of sines in order to turn them into cosines because we always remember that sine squared x plus cosine squared x is equal to 1, and we're going to use this a lot. Um, right off the bat, I'm going to show you to do this when we get to the problems, but there's the two others that we're going to remember. Okay, and I never remember them. This is how I derive them all the time, and I'll show you the shortcut in a second here. But I just divide everybody here by cosine squared, cosine squared, realizing that sine squared over cosine squared is equal to tangent squared x, cosine over cosine is 1, and then 1 over cosine, of course, is secant squared. So one of the books that I like to use in pre-calculus is called Trig or Treat. It's in our library as an ebook. So if you ever wanted to like, I really miss doing trigonometric identities, you could check that book out. It's in our library. You don't have to really go physically check it out. You can just kind of download it and take a look at it. But they usually use this abbreviation. And then when I'm doing a problem, I like to go back to the regular sine squared of x. But when I'm doing off to the side, I'll just say s and c for my things. But hey, cosine had a turn. Let's go ahead and divide everybody by sine squared and see what happens. We have sine squared over sine squared, which is 1, plus cotangent squared, because cosine over sine is going to be cotangent squared, is equal to cosecant squared. So that's all three of your Pythagorean identities that you should technically try to memorize. But like I said, I never did. But I just scratch this off to the side and then I have my identity. Okay, and I use the sine squared plus cosine squared quite often just to make sure that I make sure that my SIGN signs are correct rather than my SINE signs. Just because if it's up to me, I will probably screw up the order and mess up a minus sign in there somewhere. So knowing that we have an odd power of sine and even power of cosines, what I want to do is I want to reserve a sign because that's going to be the thing I'm going to use. And then we're going to go ahead and say this. So we want the integral of, I want sine to the fourth x times cosine squared x times, here's my extra sign, dx. Okay. And now we have the little piece that I want to deal with. Okay. So what I'm going to do is I'm going to say, okay, well, we know that sine squared, right? So I have sine squared plus cosine squared is equal to 1. Sine squared must be 1 minus cosine squared. So we're going to say, okay, so sine to the fourth, right? So we have sine to the fourth power of x, squaring this, right? Squaring both sides is going to be 1 minus cosine squared x squared. Now, this you have to multiply out. So that's going to be 1 minus, and it's going to be 2 cosine squared x plus cosine to the fourth of x. Okay, I just multiplied this out real quick like you were good at algebra. Like I was good at algebra. Okay, and we're just going to go ahead and replace this. So we can say, okay, sine to the fourth is equal to 1 minus 2 cosine squared x plus cosine to the fourth x. And then we have to go back up and collect the stuff that I still have here. I still have a cosine squared, okay? And then all of this is times, and then I have a sine x dx, and I haven't integrated it all yet. Okay, I'm going to do these mostly as indefinite integrals. If there's an a and a b here, just remember that in calculus we use radians, not degrees. So make sure that if there is an a to b, just make sure you've changed your calculator to radian mode so that you can go ahead and make sure that the class is working for you. Okay, let's multiply this out. So I have a integral of, we have a cosine squared x, that's this piece, minus 2 cosine to the fourth x, plus cosine to the sixth x, and all of this is times sine x dx. Okay, and some of you probably get a feeling of what's going to be happening at this point, because what I'm going to do is I'm going to say, let's let u equals cosine of x. And then my du is going to be negative sine of x. Hey, I've got a sine of x dx sitting right here. That's my du. So all I have to do is say, well, I need a negative. I'll put a negative here, but I'm going to put a negative on the outside because I can't just go multiply by -1. I can only multiply by +1. The two tricks in math. You can either multiply by 1 or add 0. We're going to multiply by 1, but it's going to look like -1 times -1. So I put one negative inside the integral, one negative on the outside of the integral. This little piece that I've bracketed off here, that's my du. So we're going to have our u squared minus 2u to the fourth plus u to the sixth, because cosine is u, all times du with the negative sign out there. And now I think we're set to integrate. And this is just a power rule. We could do this one. We're pretty good at this. So that's going to be -1 over 3 u cubed minus 2 over 5 u to the fifth plus 1 over 7 u to the seventh plus c. Okay, don't forget your plus c's. And then we're going to be able to just go back in and say, okay, what was this is going to be a plus, and then this piece is going to be a minus because we have minus times this. So let's go ahead and change that to a minus. See, okay, the hardest part of this is, again, your arithmetic and your signs. The calculus is not so hard, but keeping track of your SIGN signs is a pain in the neck. So make sure I got all of this right. I think we're back to normal with this piece here. So yeah, great. And then what the heck was u? U, I said, was cosine, so we can go back and deal with this. So we have -1/3 cosine cubed of x plus 2/5 cosine to the fifth of x minus 1 over 7 cosine to the seventh of x plus c. And that would be my final answer for this problem. All right. So that's how we go ahead and deal with problems like this. All right, let's see. Uh, let's go ahead and switch around a little bit. So if I have a very similar problem, but instead I have an odd power of cosines, right? So if I integrate uh, cosine to the fifth x sine to the fourth x dx, we're gonna do a very similar dance where we're gonna reserve a cosine, right? So we could say, okay, this is going to be the integral of cosine to the fourth x sine to the fourth x cosine x dx. We go ahead and deal with it this way. So it's a very similar dance where we change my cosines back into sines, set u equal to sine x, and in my du. So if I go ahead and do that just to show you, set u is equal to sine of x, du is equal to cosine of x dx. And again, this is going to be my du. I'm just going to have signs in here, so we could go ahead and replace all of my signs with all my powers of signs with u's, and then again, apply the power rule and go through it and deal with it that way. Okay, so when you have one of the powers of sines or cosines is odd and the other one is even, it's a very similar kind of a way of sorting out that problem. You reserve one of them for your du, and then you just transform everything back else into that. Okay, that's great and all. What happens if they're both even, right? If they're both odd, we know what to do. We reserve one and change everything in terms of the other one. But if they're both even, and like, okay, what if we end up with the integral of sine squared x cosine squared x dx? They're both even, and now what do I do? So this requires a different strategy. Um, One of the things I'm going to note is that the sine of 2x is equal to 2 sine x cosine x. Okay, so we could go ahead and do that. So I'll be a little bit careful with my algebra as I'm going through this, but this is going to be the integral of, let me make not quite that much room on the side here. So what I'm going to do is I'm going to break this into sine x times cosine x times sine x times cosine x. So I can do it this way. I could say we have sine x cosine x sine x cosine x dx, and we'll go ahead and figure that out. So knowing that I can replace my sine x cosine x with a sine of 2x, but I need a 2 here, but I'm going to have to multiply by 1/2 out in front because I can't go over here and multiplying things by 2. That's not fair. So I can multiply by 1. That's what we're going to do. And because it's squared, I got to do it again. So we have a 1/2 out here. We have a 1/2 in there. I'm sorry, not a 1/2. We got a 2. Okay, so there we go. So I've got a 2 here. So really now what I have is I have 1/4 the integral of 2 times 2 is 4. Actually, this is going to be, right? This is going to be a sine of 2x, right? Both of these are going to be a sine of 2x, and we have sine squared of 2x dx. Okay, so now we're going to do something called power reduction rule. And again, a lot of calculus teachers, I'm not one of them, will tell you, you should definitely memorize these. I never did. Okay, so I'm just going to work it out off to the side here, and we'll go ahead and figure out what we have to do next. So if you remember your law of your trigonometric identities of cosine of 2 theta, remember that was going to be cosine squared theta minus sine squared theta. That was one of them. There's another one. We have 1 minus 2 sine squared theta, and we have 2 um, cosine squared theta minus 1. Okay, and those were all the different ways of writing cosine of 2 theta. Well, the reason I put these up is because notice we have a sine squared theta here, and we only have a single power of cosine over on the right hand side or over on the left hand side. So what I'm going to do is I'm going to say, well, we have cosine of 2 theta is equal to 1 minus sine squared theta. We're just going to solve for sine squared theta. So I'm going to put the sine squared theta on the other side. So we have sine squared theta is equal to 1 minus cosine 2 theta. I'll put the cosine on 2 theta on this side, putting the sine squared of theta on that side with my algebra. And then there's a 2 in here somewhere, minus 2. So we have a 2 here. So we have sine squared theta is equal to 1/2 1 minus cosine of 2 theta. This is your power reduction formula. Again, a lot of calculus teachers will tell you to memorize this. I never had a problem not memorizing it and just working this off to the side. If you want to memorize it, that's great. If you want to work it off to the side, that's great. You can do it your way. But this sine squared of an angle is equal to 1/2 1 minus cosine of twice that angle. Oh, looky here. We have a sine squared of 2 thetas, 2 x's. We're going to have to double that. So what we're going to do is we're going to break this down, and we're going to say we have 1/4 integral of, what was sine squared of theta was equal to? It was equal to 1/2 1 minus cosine of 2 times this angle here. So it's going to be of 4x. Okay, dx. Now, we took calculus 1. We could integrate that. I'm going to pull the 1/2 out in front to say this is going to be 1/8 integral of 1 minus cosine of 4x dx. And we'll go ahead and sort that out. So now we're ready to integrate. I can't integrate sine squared theta this way. I can't say, oh, that's sine cubed 3 over that. No, no. Everybody, mostly you, but everybody will be very, very unhappy with that result. Don't do that. Okay, you have to use power reduction formula. You have sine squared. You have to go through this process of being able to figure this out. Okay, and you're going to do this a lot. So you might want to memorize this stuff because it's a little bit easier. But I will be unhappy. You will be more unhappy because it's going to be your grade that's going to be suffering for it, and it will suffer. Okay, so let's never, ever, ever think about doing that. Leave that to the people who just discovered integration at the end of Calc 1 and think, oh, this is easy. No, no, it isn't. It's a little bit harder than you think. But now we are ready to go ahead and integrate this. So this is going to be 1/8, and then we're going to be integrating this. So we integrate 1, that's just going to be x. And then I've got to integrate cosine, right? And integrating cosines, that's not too bad. That's just going to be sine because derivative of sine is cosine, minus, and we have a 1/4 sine of 4x here. So remember, if I take this derivative right here, just this piece, we get cosine of 4x times 4. That's where the 1/4 came in because I need, if you would need to do a little u substitution in here, like let u equals 4x, du equals 4 dx, and that's where you multiply by that 1/4. That's fine. Do this in as many steps as you need to do it so that you get it right. If you've practiced for a little while, you can probably just jump to this spot right here and you'll be fine. Don't forget your plus C, or that's the grade you're going to be getting. All right, so let me just make this come out. So we're going to have, this is going to be x over 8 minus 1 over 32 sine of 4x plus c. And again, if there's an a to b that we would go ahead and deal with, we would go ahead and look at that. Okay, so if you need to do that, that's fine. If you don't, that's okay too. All right, so that's how you deal with powers of sines and cosines. If you have tangents and secants mixed in with your sines and cosines, do the same thing you did in your trigonometric identities a year ago when you learned those. Turn everything into sines and cosines and work through it that way. Okay, that's the best advice you have. Is like, you got a whole bunch of mixed stuff to work with, but you've got sines and cosines. Turn everybody into a sine or a cosine, and then get started on the little possibilities you have here. Okay, I think that's long enough for one video, so I'm going to say thank you very much for watching the video. I'll see you in the next one, and take care.